Let's start the third chapter of this book, which is Matter and Life, which is very similar to basic chemistry. So we'll just go through this part quickly, okay, so that we don't spend a lot of time in what the things that we already know. So as we saw in the last chapter, that what are living beings? Self-sustaining chemical system capable of Darwinian evolution. Self-sustaining chemical system. So when we talk about chemical systems, similar to Democritus, we'll just be talking about matter. So we are made up of those things that even the non-living things are made up of, right? Just matter, elements, compounds. So let's start with the concept of elements, which we already know. So an atom, right? So an atom made up of the nucleus and the electrons. The nucleus has the positively charged particles, the protons, the neutral particles called the neutrons, and then the electrons are orbiting it. The charge on the nucleus is positive because of the protons. Neutrons they don't have any charge, and the charge on the electrons are negative, right? Now, the protons and the neutrons, they have mass in this order. The neutron is slightly heavier than the proton, and then the electrons are about 2000 times less. So it is 1/1827 or something like that of the mass of the proton. So it's very, very light. So as compared to the protons and the neutrons, you can say that electrons are almost weightless, massless, something like that. But they do have some mass, okay? The atoms typically are neutral. So the positive charges cancel the negative charges. What is the utility of the neutrons?
If many positively charged protons are staying together, so there should be another particles to give them the stability.
So why can't the protons stay together and be stable?
Because they all are positively charged, so they connect with each other.
So electrostatic repulsion in the nucleus makes the nucleus unstable. That is being countered by the presence of the neutrons. Okay? So you can think of very simplistically as so there are different kinds of forces, right? So okay, so when we are talking about the solar system, what is the most fundamental or most important force that we think about? The gravitation, right? So long range order forces, like where we are talking about astronomical distances. Now, when two things of any mass are together, they exert a gravitational force of attraction towards each other, and gravitational force is always attraction. There is no gravitational force of repulsion. So I am attracting the computer is also attracting me, but that force of attraction is not super strong in this case. What keeps the planets in motion, that staggering amount of force, is not the most important force between us right now. So you have to keep in mind that there are forces of nature that become more important given the context. So there is another very important force of nature called the electrostatics. So the charge of attraction or repulsion between charged particles. So between two there is a force of repulsion between two charged particles of the same kind, positive or negative, and there is a force of attraction between a positive and a negative charged. So sometimes those things will become more important. Okay, so in here you will see that electrostatics becomes really important. Okay, so there is a huge charge of repulsion that is going on. In order to counter that, the neutrons are coming in, right? And in this particular case, when we are talking about atoms and nucleuses, nuclear forces, and I'll not get into that, also become really important. What happens typically is this. So protons and neutrons will have their own masses. Okay, when you get all that mass together and you add them up, you will see that the actual atom that it is made up of is slightly less in weight than the summation of the protons and the neutrons. That small change, so say a carbon atom is made up of 6 protons and 6 neutrons. You add the mass of the 6 protons and 6 neutrons and then check a carbon atom, you will find that the carbon atom weighs just a little bit lower than the cumulative of the 6 protons and the 6 neutrons. That small dip in energy, that small decrease in that mass is actually making them stable. You can actually calculate that by E is equal to mc square. Okay? Every nucleus will have its own nuclear stabilization energies, and we kind of saw that in geochemistry, in chemistry of the solar system. Okay, not getting into that. What I wanted you to know is recapitulate whatever we already know about atoms and molecules. Okay, now there are also isotopes of atoms. What are the isotopes? What are isotopes? What are isotopes? Same, iso means same. Same protons. Same protons. So when you have same protons, will your atomic number be the same? Yes. So you have the same atomic number. But what is different then? The number of neutrons. That means 2 atoms that have the same number of protons but different number of neutrons will make an isotope pair. Okay, so same atomic number, different mass number, because the mass number is protons plus the neutrons. For example, carbon. So you have C12, in which you have 6 protons, 6 neutrons, C13, 6 protons, 7 neutrons, and C14, 6 protons and 8 neutrons. So whenever you have 6 protons, the chemical identity of that atom is fixed. So whenever you have 6, anything that has 6 protons, without even knowing how many electrons or how many neutrons, you have to say out loud, it is carbon. That's it. If it has 6 protons, without knowing anything else, you can say it is a carbon atom. Okay, so all these 3 are carbon atoms, but they have different number of neutrons. Why is this important in life or in astrobiology? Isotopes. So there are 2 types of isotopes. What are the 2 types of isotopes?
Stable
And
radioactive.
radioactive, right? So one in which the nucleus is stable, the one which is not. So the carbon isotopes are what? They are stable or unstable or radioactive.
C14 is radioactive.
C14 decays, right? C14 decays. C12
Is stable.
doesn't decay. Okay? So C14 decays at the rate of 5,830 years or something like that. Okay? So every 5,000 or 6,000 roughly years, there will be a decay. So that carbon nucleus is going to decay into something. Let's not go into the process of the decay. But yeah, there are some radiogenic isotopes, there are some stable isotopes. In life, how can these two isotopes be important? Or how can they be important for us to study life or study astrobiology? The isotopes, how will they come into play?
So life is carbon based.
As life as we know is carbon based, yes.
In those carbon compounds, they are maybe the stable isotopes and the radiogenic isotopes mixed. So, and the radiogenic isotopes is decaying, they are decaying. So, if we found a trace of radiogenic isotope in some point of time, we can tell how, when it is formed or when the life is started. At that time, maybe
carbon dating.
Of radiogenic isotope.
Carbon dating, right? So we can do carbon dating on living organisms that we know were living, and then we can say how early it existed. So the practical application, carbon dating. What else? Okay, tell me whether life is picky or choosy, or it doesn't matter. Imagine life to be like an organism. Will that organism be picky or doesn't matter? It will be picky. It will not like everything. It will have its preferences. Okay? In chemical reactions, will life prefer a lighter isotope or a heavier isotope?
In metabolism, the complex molecules are it's like breaking down to the simpler, and that is essential for our uptake of nutrients. So maybe some lighter elements, lighter compounds.
What do you guys think? Why would it prefer lighter?
It's more stable.
It could be. Yeah, that's good. It is stable. Also, because it is lighter, it's easier to move. Very simplistically, if I have to think about it. So life in general, but I might be wrong in some cases, but in general, we'll see life preferring lighter isotopes to heavier isotopes. So if there is a chemical process that is being done through non-biological process versus a biological process, we will typically see that the biological process is going to favor the lighter isotopes than the heavier isotopes. And we'll see this later. Okay? But the isotopes become important in this regard. Now, these could be isotopic tracers to detect life. For example, if you found a carbon compound which has a typical isotopic signature of light versus the heavy, it could potentially be used as a chemical signature of life being present or not by studying their isotopic ratios. Okay, so that's the power of the isotopes. Okay, now we also saw a lot of these atomic structure things in geochemistry, right, or chemistry in general. So I'm not going into that, SPDF and all those kinds of things, right? So I hope you guys remember that, right? Now let's move on to bonding, because it is not only necessary for the atoms to present, it is also important for different atoms to form bonds and then form stable bonds so that life is stable, right? So you cannot just have atoms, you need stable bonds between those atoms. The different bonds that we'll see are these, okay, in nature, not in life. I'm just saying the different bonds that we generally see are ionic, covalent, metallic, and then we see these van der Waals interactions and the hydrogen bonding. So we studied a lot about the covalent bond and the ionic bond, right, and these kinds of things. So in here we'll just see some examples of these different different types of bonds in life, and then see which of these is not possible. Okay, which of these do you think does not matter for life? Or we have not seen these kinds of things in life? Of these 5: ionic, covalent, metallic, van der Waals, and the hydrogen.
Which one is not important?
Not important. Okay, let's go step by step. Okay, let's see ionic bonds. So ionic bonds are very simple, right? So there is a exchange of electrons. Okay, so if there is one atom, and all these things can be simplistically explained by the octet rule, which the atoms are trying to achieve an octet. So for example, very simple example, sodium chloride. So you have a sodium atom with an electronic configuration, simple electronic configuration, 281. Right? So if it leaves one electron, then it becomes 2,8, becomes stable. So this metal, sodium, has a tendency of losing electrons, versus chlorine, which has the electronic configuration 287, has a tendency of gaining one electron to become stable. So this is a good kind of agreement between these two different atoms that they come up with. Sodium says, hey, take my electron, chlorine readily takes it, but they stay kind of close together. This kind of arrangement is called an ionic bond. All the different kinds of salts, things like that we see is this ionic bond. Okay, strong forces of attraction. All right, now in nature, we will see these kinds of bonds in any time you have charged species, where there is an electron transfer. You will see ionic bonds. So for example, this is lysine. Lysine is an amino acid. So you will see that some people in our lab are also working with different kinds of amino acids. What's an amino acid? Have you heard about amino acids?
It's a carboxylic group and amine group present.
Okay. Do you know anything that is made up of an amino acid? The protein, the muscles that we have are basically made up of. So they are the monomers of our protein polymer. So our proteins are polymers, think of that, and these are the monomers. These are the building blocks of the proteins. And these are typically amino acids, in which you see this amino group in here, which is NH2, and this is a charged amino acid that we are seeing. So typically you will see a COOH group, right, and which is like clearly seen here. The COOH. The H is now gone, producing the minus. Because it is a carboxylic acid group, that COOH lost its H, or donated its hydrogen or the proton, and that's the amino acid part. So any amino acid, any acid or any carboxylic acid will be of this COOH making. And any amine will be that NH2. So this COOH group is the carboxylic acid group which donates the proton, and the amine is something which is basic in nature that accepts the proton or donates the electron. The N with that lone pair on it can behave as a base. So amines are bases, carboxylic acids, as the name goes, are acids. These are two separate. You could have a carboxylic acid. Right. For example, the acetic acid, the vinegar that you have, that is CH3COOH. So that is a carboxylic acid. Amines, you could have a CH3NH2, that's methylamine. But there are also groups like the amino acids which have both the amine and the COOH groups. The good or the great thing about that group is they can act as what we call as Zwitter ions, in which the same compound has a COOH group, which is the acid, and the same compound has a base, which is the NH2. The H plus can be transferred from the COOH to the amine group. Making sense? or not? So say you have this is the acidic part, right? COOH. And this is the acidic H. What is the acidic H? An acidic H is that hydrogen that is attached to an electronegative atom, right? So oxygen is attached, so hydrogen is attached to the electronegative atom O, so that becomes the acidic H. Now this H can be released and go and attack here. So what we'll end up having is, what does this become? What is the charge on this? When it loses, and this becomes an NH3 plus, right? So the same compound has a plus charge and a negative charge. So this is called a Zwitter ion, ZWITTER, Zwitter ion. You can see this kind of thing happening in here, but in this case you are seeing two different amino acids in function. So one is lysine, this is a name, in which the NH3 plus is here. How did it become NH3 plus? From like this, in here. And the COOS minus from the aspartic acid. So this is not an, it's a different group, right? But it has the COO minus. These plus and minus between these two different groups will form an ionic bond, right? So this is something that happens in life in our systems, okay? We also will look into the salt bridges concepts, right? So like sometimes these can act as salt bridges. So ionic bond in life is very common. Covalent bond is very simple. It's just the sharing of the electrons. Equal sharing. There is no transfer of electrons. It's like one electron from one atom, the other electron from the other atom comes together and they form a covalent bond. Okay? So this is very simple, and we see covalent bonds everywhere. For example, if you see any organic matter with all these dashed lines, these are all representative of one covalent bond, right? When you see two lines, that means it's a double bond, right? So there are two pairs of electrons that is being shared. 3 pairs is also possible, right? So all these kinds of things are possible, and they are very much essential for life to be stable. These are very stable, right? We'll also see like covalent bonds in microbes, and you will see, I don't know if they are showing, yeah, these disulfide bridges. See these disulfide bridges, these are extremely stable. This becomes very important in many microbes, right? These disulfide bonds. So this is just an example in which they are covalent bonds, and these colors are due to what? Iron, right? And different kinds of, but iron plays a really important role in pigmentation of these. But all these are covalent bonds, okay? These examples. Now, metallic bonding. So we saw metal and non-metal, when they come together, they make an ionic bond. When a non-metal comes together, they form a covalent bond. But what happens when a metal and a metal comes together? We have metallic bonds. They do not form ionic bonds, because even if one metal transfers its electron to the other, still there is a dearth of electrons. You cannot have all 8 valencies satisfied. You cannot have a stable octet, right? Similarly, it will not be able to have a covalent bond, because even if you share one electron, you still don't have the stable octet, right? You need a special arrangement called metallic bonding, in which there is one, so this becomes like a co-op, like a cooperative society, in which everyone comes with their 1 electron or 2 electrons. So imagine all these sodium atoms coming together in a meeting like this and say, hey, take my one electron for the community. And in return, what they get is immense stability, because when thousands and thousands and millions and billions of these atoms come together and they donate their electron, what happens? They create a sea of electrons. And in that sea of electrons, every individual sodium atom can have its 8 electrons. It is sharing, but it now stays in that sea, in this pool of electrons all the time. And that is the metallic bonding. Okay? This is not relevant for life. We don't see things like this. Although we need metals, we need iron in our body, hemoglobin has it, right? And there are so many other essential D block metals. Of course, there's sodium, potassium, all these things are very important. But we don't find a metallic bond in life. Okay, it's not that common. Okay, now there are all these simplistic interactions called the van der Waals interactions, and we will look into the van der Waals interaction in the next class. Okay, so we ran out of time, so we'll look into the van der Waals interaction. We'll look into the types of van der Waals interactions, and we'll also look into the types of hydrogen bonding, or where the hydrogen bondings are important. Okay, cool. So let's stop it here.